We're continuing here our work on capacitance, chapter 24, and we're going to be looking here in this module, which is 24.3, at dielectric materials. Now, a dielectric material is some material that is going to have various properties when it experiences an electric field. For example, paper or wood or water will have its atoms reorient. Let's imagine that we think of a parallel plate capacitor here, and normally we've been up to this point looking only at a vacuum at these equations. And you recall our equation said that the capacitance was Q divided by the voltage. But now let's take this same capacitor where, you remember, if we take charge Q and put it up here, if it results in a voltage V, this thing has a capacitor C. But now let's put something in between. Just for an example, let's imagine we put water here. If we put water between these two plates, remember one of these plates is going to be positive and the other plate is going to be negative. But water has polar molecules, and those molecules are going to turn around so that the negative end aims downward, the positive end aims upward. And even if it were not water, where the molecules could actually turn some and reorient, in other types of materials, let's say if we had a molecule here, the positive charge in this molecule would be pushed to this end, the negative would be pushed to this end, and in both of these cases you can see that what you get is a diminishing of the electric field between the two plates. Therefore, the capacitance is altered if you put a dielectric material in. How is it altered? Well, it turns out that the equation is V is equal to V naught divided by K. In other words, the voltage that you would have had otherwise as V naught, if it's empty, is now altered by a constant kappa. So we write V is equal to V naught divided by kappa, the Greek letter kappa, where kappa is called the dielectric constant. Kappa is equal to 1 for the vacuum or air. But it's 3.7 if it's paper, 80 if it's water, so water has a very high dielectric constant. Now because of this, when I now move a charge Q and end up with a voltage V, you can see that if I plug this in here for the new voltage, I get a capacitance which is Q divided by V naught divided by kappa, so I end up with kappa here. But this was the original capacitance, so this is K times the original capacitance of the system. And so if you remember this formula, it's very easy to realize that kappa, being a number greater than 1, is going to lower the voltage. I now have a reduced voltage. When I plug that into the capacitance, I end up with a higher capacitance. So we end up with the second formula, C is equal to kappa times C naught, where kappa is the material that I have put in, called dielectric material, that I've put into this particular capacitance. Obviously, a lot of different materials can allow the capacitance to become much larger if you put them in there.